welcome back to J Club, and for today's video we're going to be discussing on a rather peculiar topic and also a branch of mathematics, the Fibonacci sequence. And today from the Tweet Like a J channel, we're going to be discussing, I'm going to be telling you the significance and importance of this topic and why mathematicians have been struggling and striving to get the answers and the methods to this very and rather interesting topic that has very relevant mysteries towards nature, and also another topic we're going to be discussing later on. So what is the Fibonacci sequence? For people who don't know them, it's quite famous enough for people to know. It's quite a celebrity, not as famous as E equals MC2, but still famous. And to people who don't know it, I'll be showing you a pattern. I just showed you just now. It was 1. Now you can look at this pattern and try to examine what is the pattern in this sequence, and you probably got what it is already. 1, 2, 3, okay, we 4, just kidding, 5, and then 8, 13, 21, 34, 55, and so on. So what does this sequence do? Imagine this. The Fibonacci sequence is a series of never-ending numbers, okay, so the pattern never ends, that are produced by two sets of numbers before it as a sum. So what does this mean? 1 plus 1 equals 2. 1 plus 1 equals 2. 1 plus 2 equals 3. 2 plus 3 equals 5. 3 plus 5 equals 8, and so on. So you can pretty much draw an arrow over here, and it will make it much more easier to comprehend what's a Fibonacci sequence. So in my opinion, the Fibonacci sequence is very mysterious in some way, because this is how the as mathematicians say, some ways that the universe works. Sorry about that. And I believe this is true because 1 plus 1 equals 2, 1 plus 2 equals 3, 3 plus 5. The fact that it's that kind of way is just beautiful. And what I see I just drew this chart, and I found something weird in this. It's that 1 and 1 are the same, 2 and 2 are diagonally the same, and 3 and 3 are diagonally the same. Oops, sorry about that. This means that what this actually means is that in every Fibonacci sequence, the identical number is repeated thrice. One in its answer, the other in its addition, and the other in its also addition. So it's 1 plus 1 equals 2, that's the answer, and then 1 plus 2 equals 3, and then 2 plus 3 equals 5, and then it's gone. So the 2 is represented 3 times. 1 is also represented 3 times here. 5 is also going to be represented by adding 5 plus 8, 13, and 13 plus 8 plus 13, 21, 13 plus, 21 plus 13, 34, 34 plus 20, 21, 55, 55 plus 34, 89, and so on. So you can pretty much imagine the Fibonacci sequence in this way. And there are many actually examples to the Fibonacci sequence, and I want to gather some examples in nature so that you understand why the Fibonacci sequence is quite coincidental, even though it was discovered in the 1st century and the 2nd century by Leonardo Pisano, who didn't have any idea that this was applied in logical nature problems. And some of the examples include flower petals. Of course, those sunflowers, nice. I like sunflower seeds. And you can actually see that all the flowers in this world, yes, I mean it, all the flowers in the world except for some flowers with weird DNA structures, I don't know, have the same not the same, but the number of petals as the Fibonacci number. So some flowers have 21 to 55 petals. If you go back here, 21 to 55, they're both Fibonacci sequence. 21 to 55, so 34 is also in the middle, which is the Fibonacci number. And then hibiscuses have 5 petals, which is a Fibonacci number. And lilies have 3 petals. Of course, that's also a Fibonacci number as described before. And the other example includes flower seeds, and of course you can see here, but too tiny to see. Blame my eyes, not the picture. Now flowers have 144 seeds. There have been counted, which is not shown actually in here, but if you can do the math, then it's pretty easy. So after 55 plus 34 is 89, and 55 plus 89 equals 144. So 144 is also a Fibonacci number, and I could go on about zany things and flower seeds, but let's not go about that. But let's just stick on to the sunflower thing. And the other example, which is the last one, is spirals. Now spirals, to understand this, you need to understand another portion of the Fibonacci sequence. Okay, let's just read the description. The spiral movement, now this is one we're gonna discuss about soon, is inclusive in seashells, like those spirals, and also in the range of flower seeds, like how they're structured. So this is how flower seeds are structured here, and then there's spirals over here, spirals over here, spirals over here, and then the spirals create another spiral, and then this spiral creates another spiral that is a spiral inside a spiral. And take an example of this. So according to the Fibonacci number, we're going to have a unit of squares. Let's just say 1. 1 is the first Fibonacci number. So we have 1 unit square. So 1 by 1. Then it's a 1 again. We put on another 1 again. That's because there's 2 1s in a Fibonacci sequence. After that, 2. Then a 3. And then a 5, and then an 8. I'm not sure if you can see here, but anyway. Okay, so and then 8. So we have a rectangle here, right? Now, what if we started from this point and we linked these points together? Then we drew something like this. That will be a spiral, right? And the spiral movement is actually present in this as well, and in also many other things like seashells is described. So yep, that's a picture of it, just to prove the fact. Yep. And that spiral movement is just amazing. It's like this and then that. So spiral movement. So you link the tips together, and what you get is a spiral. Now, although these examples may seem very amazing and why we are learning this, but even this to scientists are just meh. So why do we learn this? And this is because of the golden ratio. The golden ratio. Yeah, the golden. Maybe the golden ratio weighs like 1,000 pounds of gold, and you sell it in the gold shop for like, I don't know, $1,000 because it weighs 1,000 kilograms. Now the golden ratio actually is a ratio in it, which it's not really a constant, but it's like a decimal place, which is equal to about 1.618, and it's represented as the symbol phi or phi, and it's the symbol. And why this is so relevant to the Fibonacci sequence is just a coincidence, or it's just a law of nature. Now take this example. Let's say we divide the Fibonacci sequence numbers by the opposite direction. So it's a 1 divided by 1, and then 2 divided by 1, and then 3, and then 3 divided by 2, and then it's 5 divided by 3, and then it's 8 divided by 5, and so on, like this. Yeah, until 13. Yes. Now, let's discuss the answers. I mean, getting the answer is not really important, but the answers are. So let's just say 1 divided by 1 is 1, 2 divided by 1 is 2, 3 divided by 2 is 1.5, 5 divided by 3 is 1.66666667 or something. 8 divided by 5 equals 1.6, and 13 divided by 8 equals 1.625. So there you have it, those numbers. Now, let's say the golden ratio is about 1.618. 1, 2, 1.5, 1.6666, 1.6, 1.625. So every time there's a transition in division, it gets closer to the golden ratio. Although it never actually reaches the golden ratio, it gets closer and closer and closer. Or it also gets closer to the inverse of the golden ratio, aka 0.618. But that's rare. This is more common. It's like 1, 2, 1.6, 1.5, 1.666, 1.6, 1.625. You can already see that 1.625 is actually very close to the golden ratio. And this is just a coincidence that has struck together with the Fibonacci sequence and the golden ratio. I'm pretty sure Leonardo Pisano didn't make that out with the golden ratio. It's like, hey, I think something starting with F should be at the title of the golden ratio, and they just invented the Fibonacci sequence. He didn't. So we might as well think that the scientists and the mathematicians inside the world have actually created things that have led to such big mysteries that we still wonder about today. And by making this video, I'm not going to ask you to subscribe. I just want to tell you that that discoveries aren't made by just saying, oh, I think there's a bacteria here. Let's just invent a bacteria. It's relevant. So if you create, for example, something called B, something called A, something called C, something called T, something called E, something called R, something called I, something called A, then you form these together to make a bacteria. And then you form things to create bacteria, and then you have a bacteria, and you create something called a virus, and a pandemic, pandemic, and a face mask, and then a face mask equals staying at home, and then staying at home equals watching this video. Thank you for watching.